Another thing that stoichiometry is useful for is when we look at a reaction that focuses on the heat that's produced or absorbed by the chemical reaction. For example, burning propane. I think we've seen this balance reaction before. C3H8 propane reacts with oxygen, and that forms carbon dioxide and water. Most likely the reason people are burning propane is not to produce carbon dioxide or water. Propane tanks are used to produce heat. So we could say that heat is another product, even though it's not a chemical. And this heat being released means we have an exothermic reaction. We've talked about endothermic and exothermic reactions previously. We were using Q for the heat, and Q is directly related to a quantity which is delta H. It's called the thermochemical equation when you include the value of delta H. So you'll see this balanced equation written, and then next to it you'll see the value of delta H. And delta H is negative 2044 kilojoules. So heat is Q, and Q, heat, is approximately the same thing as delta H. This is called the change in enthalpy, but when you see delta H, you can just focus on heat. So when we write the balanced equation with delta H, we have this thermochemical equation, and this implies that the amount of heat is going to change when the amount of the chemicals change. If you burn a little bit of propane, you're not going to make as much heat as if you burned a lot of propane. So this delta H, this heat or enthalpy number, tells us how much heat would be released because it's negative. Remember, Q is negative or delta H is negative. That means heat is released. It's exothermic. And the key conversion factor that we're going to use is the number of moles from the thermochemical equation matches up with the delta H. So for example, the coefficient on propane is a 1 in this balanced equation. 1 mole of propane would release 2044 kilojoules of heat. If we reacted exactly 1 mole of propane, that's how much heat would be released. If we were interested in the oxygen instead, it would be 5 moles of oxygen would have to react to release the same 2044 kilojoules of heat. If we were looking at the water that was made, it would take 4 moles of water to be produced, and then we know we would also be producing 2044 kilojoules of heat. So this thermochemical equation doesn't look like a conversion factor that we're used to, but remember, conversion factors have 2 units, and the 2 units, one of them is the moles, which is from the coefficient of the balanced equation, and the other one is the kilojoules in the delta H. So for example, if we make 758 grams of carbon dioxide from this reaction, how many kilojoules of heat would either be released or absorbed? Well, we know delta H is negative, exothermic, so we know it has to be heat is released in this reaction and not absorbed. And our unknown, how many kilojoules of heat, we set that equal to the amount of carbon dioxide. And we want to use Our conversion factor, the 3 in front of the carbon dioxide, remember, is moles. So right now we're starting with grams, so we first have to turn grams of carbon dioxide into moles of carbon dioxide using the molar mass from the periodic table. And then once we have moles of carbon dioxide, we can turn that into kilojoules of heat from the thermochemical equation. 3 moles of carbon dioxide releases 2044 kilojoules of heat. So we get an answer of negative 1.17 times 10 to the 4th kilojoules. Now, when you read that out, you don't say that we lost negative 1,000 or 1.17 times 10 to the 4th kilojoules. You don't lose negative heat. The sign of delta H tells you whether heat is being lost or not. So delta H can definitely be a negative number like it is in this case, but we would say we lost 1.17 times 10 to the 4th kilojoules. Endothermic and exothermic reactions, we're already familiar with those, so you should also be able to look at some pretty simple examples of chemical reactions or physical changes and determine whether they are endothermic or exothermic. So for example, ice melting. We have a phase change, so it's a physical change from water solid to water liquid. Heat will either be added to the reactant side or released from this reaction. So if you think about ice turning into liquid water, do you have to put it into the freezer to take away some of its heat, or do you put it into a hot oven and add heat to it? And obviously you have to add heat to the ice to make it melt. So heat is on the reactant side. That makes this an endothermic change. And just like Q positive means endothermic, delta H follows exactly the same sign convention. An endothermic reaction always has a positive delta H. The next one, nail polish remover evaporating. We're starting from a liquid and we want to turn it into a gas. So same questions, just like looking at the ice, and you have to add heat to the liquid to make it evaporate. So this is also endothermic, positive delta H. And then the last one, burning gasoline. Now, you might think about adding a match to some gasoline as being endothermic because you're adding heat to it. But the chemical reaction produces much, much more heat. And if heat is being produced, this is exothermic. And delta H for an exothermic reaction always has a negative sign.